What we'll do today is probably some of these things were covered last time. How to draw a free body diagram, how to write equations of motion, and then find things of interest like acceleration, velocity, and so on. So sometimes we want to express the motion of the particle in terms of rectangular coordinates, x, y, and z. In this case, what you do is you write the equations of motion in rectangular coordinates. So equations of motion in rectangular coordinates. So an example would be falling under gravity. So we can write three equations for the three coordinate axes. Summation fx is mass times acceleration in the x direction. Summation in the y direction for the forces is m times ay. And summation of forces in the z direction is m times az. And these forces F are all external forces. So forces from gravity, forces from a spring, and so on. Okay, so the recipe for solving for acceleration and eventually position and velocities is the following. Recipe for, this is called kinetics, which is F equals ma, and kinematics is what we covered last chapter, which is how to find the position and velocity given the acceleration. So the recipe is the following. Draw a free body diagram. Okay, then write equations of motion. So that would be F equals ma. So there'll be F equals ma in x, y, and z. And then this part is optional and really depends on the problem you're solving. Sometimes you want to find the velocity or position. What you do in this case, you integrate the acceleration to get the position or velocity. So if you are asked for S or P, then integrate A, I'll say A's from 3. Okay. So it's very important to draw a free body diagram because sometimes you know what the equations will come out and you just tend to write, but many times people just miss certain forces if they don't draw a free body diagram. And I would highly stress on drawing free body diagrams because there will be credit at each and every question where there's a free body diagram involved for drawing free body diagrams. If you don't draw free body diagrams, you will not get full points. Okay, this is one of the important skill of this class is to be able to draw a free body diagram. Okay, it doesn't have to be beautiful, it just has to be convey the information. Okay, so little bit about drawing free body diagrams. Free body. So I'll abbreviate this as FBD. So the problem is there is a mass on the ground. This denotes the ground, and it's pulled with a force F as shown. You're told to draw the free body diagram. So the FBD would be. So what you do is, so there can be an FBD for. There are three FBDs really in this case. There's an FBD for each and every particle. So There's an FBD for the mass, say, there's an FBD for the ground, and there can be an FBD for the mass and the ground. So if there are two bodies, there'll be three FBDs, and you don't have to draw FBDs for every single particle. You just have to draw it for things which you think are important in order to solve the problem. So FBD for the mass would look like this. So I'm just drawing the mass. I'm removing the ground from the figure and replacing the effect of the ground with a force. So what the ground is doing is applying a force in the normal direction. And why is that? Is because if there was that force did not exist, then the mass would just go into the ground, right? It will penetrate the ground. So there should be a force. There is mg acting downwards. So I can draw it here if you like. So for particles, it doesn't matter where you put the forces because there's no rotation. But when you have rotations, the point of application of the force is going to be important. So for this part, you don't have to worry about the exact location of the force. I just put it there. Really, it acts from the center of mass, right? So you want to draw the free body diagram for the ground. I've removed the block from the ground. So because the block exerts a force, well, since the ground exerts a force N on the block, there should be an equal and opposite force on the ground, right? And then if you want to draw a free body diagram for this entire system, so that would be the free body diagram for the entire system. Yeah?
Is there friction?
There's no friction. Okay. Good point. No friction. So if you're not told about friction, just assume it's to be 0. It makes your life simple. So FBD for M, FBD for ground, and FBD for M and ground. Okay. Now, something like this is incorrect. If you draw if you say this is the free body diagram for the mass M, FBD for M, then this is just wrong.
So you only want your net force for your system?
No, so the reason why this is incorrect is because the ground is exerting a force on the particle which you have shown here, but you've also shown the ground. So you can either show the ground or you should replace the effect of the ground with the force. So in this case, if I removed N from this picture, this is a correct FBD for well, I think yeah, so this would be an incorrect FBD. If this has to be an FBD for the complete assembly, then there shouldn't be mg or n. Okay, so don't do this mistake. This will be marked wrong. When you have two things sticking together, holding things together, and when you remove them apart, that is the time when there'll be forces between them. The moment you put them together, there's no forces between them. Well, there are forces, but they don't show up in the free body diagram because they are internal to the particular assembly, right? So, for example, if you want to draw a free body diagram of me, okay, there are internal forces. There are forces holding my arm in place, but that does not show up when you draw a free body diagram of me. So the moment you remove my arm apart, there will be forces which you need to show. So when things are combined, don't draw forces. They only show up when you pull things apart. Okay, this is very important. The most common place where people make mistakes. So what we'll do today is essentially follow this recipe. Okay, draw free body diagram, write equations of motion, and solve for kinematics as needed. Any questions on this? Okay. Okay, so if a force F is applied on which is 150 newtons. 150 newtons as shown. Determine the velocity of the 50 kg block. So this thing is 50 kg when the block has risen by 3 meters starting from rest. So you've told that it's been told that this block moves 3 meters up starting from rest. You're going to find the velocity of the 50 kg block. So V is how much when this block moves up 3 meters. Okay. So where have you seen such a problem before? Where you have pulleys? It was probably in the chapter 12. In that problem, you were given velocity or acceleration for B, right? And you're told to find the velocity and acceleration for A. But in this case, you're told that there's a force which is applied at B. So you cannot just use what you learned in 12 here. You need something more. You need F equals ma because you're told that Fx on B and not just acceleration or velocity. So we'll follow the recipe, which is draw the free body diagram. So there are a number of things here. There are 3 pulleys, there is a mass, and there's those things are connected to the ground. So you can draw, I guess, a lot of free body diagram. You can draw a free body diagram for each of the pulleys. You can draw a free body diagram for mass, for the ground. You can take 2 pulleys together, draw a free body diagram. There are lots of free body diagrams you can draw, but you want to only draw free body diagrams of things you care about. So what I would recommend if you have too many bodies is to just draw free body diagrams for individual objects instead of trying to combine and draw free body diagrams. If that doesn't give what you want, then you can think of combining things. So if you want to start with free body diagrams of individual objects. So I'll start with let's call this. So A, B, C, let's call this pulley D, and let's call this pulley E. So let's draw a free body diagram for E. So given that there's a force F acting downwards, so now I'm also going to, so at this point here, there is a string. And one thing to note is the string can only transmit forces along its length, right? It cannot transmit forces perpendicular in any other direction. Why is that? It's because when a string, when there's weight here, the tension always acts along the string. It doesn't act this way or that way. So the force has to always be in the direction of the string. So the forces in this case are going to be in this direction. And there'll be a force here. Now, because it's an inextensible string, the forces get transmuted. The force here is the same as the force here and so on. So the force here on the left side is the same as the force on the right side. Okay? And if you like, you can call that a new force over here. But really, if you see the figure, you notice that that force over here is just 2F, right? It is 2F because, well, that pulley E has no mass. It's not given to you, but I think since they have not said anything about the masses of the pulleys, it's assumed to be 0. So as long as those pulleys don't have mass, then this is fair. This is 2F. If this pulley had a mass, then that would not be 2F. You'll have to write F equals ma in the vertical direction and find the force. Okay, so then let's draw the free body diagram for C. Okay, this is C, and so there'll be a force along the string in the upward direction. It will be equal and opposite to the force I've drawn here. This will also be F, and this force here is going to be what? What's the force here? It's 2F. Again, it's 2F only because C has no mass. Okay, then we can draw the free body diagram for D. Okay, this is D. Again, there's a string here, which basically this string here is the one which I've drawn over here. So this force is going to be 2F. So this string wraps along this pulley, and so there's going to be another force which will be equal and opposite to F. This 2F is from here, and then this force is going to be what? It's going to be 4F. Okay, again, this is true because D has no mass. So what I've done really is I've applied F equals ma on that particular figure without really writing it down, just to make I don't have to write that equation separately because it's very trivial. But if that had a mass, I would write F equals ma, and then you'll see that that force here is not equal to 4F. It depends on the mass and the acceleration of D. So I'm left with only A. So this string here is applying a force 4F, so there's going to be an equal and opposite force 4F on the mass, and then mg acts downwards. Okay, so those were the 4 free body diagrams for the 4 things here, 3 pulleys and 1 mass. So next we can do is write equations of motion, and really we've sort of already written the equations implicitly for the pulleys. We already used that fact to write those forces. So the thing we have to do right now is only write the equations of motion for the mass. So if this is y, then Fy is may. So the net force, again, this Fy is the external force. So the external force is 4F acting in the positive direction. There is mg acting in the negative direction. And then there is mass times acceleration y, which is acting in the positive y direction. So this mass is moving up, right? We're told that it moves up. Okay, so we are given the force. We are also told the mass is 50 kgs. Gravity is 9.81 meters per second square. So I can solve for the acceleration. So 4 times 150 minus 50 times 9.81 equals 50 times AY. And if you do the math on that, AY is 2.19 meters per second. Meters per second square. Okay, so we have to go beyond this because we have to solve for the velocity of, find the velocity of block A. So we're going to find the velocity of block A. So this is only giving the acceleration. So we need to do the next step, which is the optional step, which is do the kinematics. So kinematics. So we've been given that the block A moves from rest by a distance of 3 meters. We're going to find the velocity when the block has moved 3 meters. So there are 3 formulas, right? What are 3 formulas for the kinematics in the y direction? There's one which says S is ut plus half at square. There's one which goes v square minus v0 square equals 2a times s. And the third one is V equals U plus AT. And since we are not interested in time anywhere here, we'll choose the second one which I mentioned. So the one we'll use is Vy square minus Vy0 square is 2Ay S minus S0. Okay? Because I'm not interested in the time. So the velocity, initial velocity is 0. The initial position is 0. Vy square is an unknown. 2Ay is 2.19, and the distance moved is 3 meters. So Vy comes out to be 3.62 meters per second. Okay. So here's the next question. So the force of a motor M, so this is the motor, on the cable is shown in the graph. So this is a plot of the force. So I think they imply that this cable here applies a force F, which is a function of time. The function is 625 t square. You got to find the velocity of the 400 kg crate A. So this is a 400 kilogram crate when time equals 2 seconds. Okay, so the reason why you would want to do FBDs for this is because, again, you're given forces and you're told to find velocity. Okay, since you're given forces and told to find velocity, this is a free body diagram problem, Newton's laws. Okay, so since we know that we need to do FBDs, how many particles we have? We have 2 pulleys, we have a motor, we have the block, and a lot of particles. But in this case, what we can try to do is we'll try to think about what we are really interested in, which is finding the velocity of A. So let's draw a free body diagram for A, and then try to see if we can find the acceleration of A. If we cannot, then we'll probably need to draw another free body diagram and keep doing that till we can solve for all the unknowns. So let's start with a free body diagram for A because we want to find the acceleration of A eventually. So this is A, and what I'm going to do is I cut this cable here, and so that's I'm going to replace the effect, the cut with a force or a tension. And there's mg acting downwards, and my convention is going to be upwards is positive. Okay, so if I write F equals ma for this mass, then let me write this as mag. If I write F equals ma, that equation will have a tension T coming in, and I don't know what the tension is. So I just cannot use only this free body diagram to solve for the acceleration. I need to go a step further, that is find essentially T. So if I want to find T, I need to draw a free body diagram for this thing. So this pulley. So let me call that pulley B. Say, so for B, there's tension acting in this direction because here you can see that the tension was acting in the upward direction. So since the cut is made here, the tension for that pulley is acting downwards. Okay, so since I cut it over here, and since this pulley has no mass, I can write this to be T divided by 2 and T divided by 2. And the only reason, again, I said is that pulley has no mass. And so the sum of the forces in the vertical direction should add up to 0. Okay, is that clear? Okay, that does not still help me to solve for the tension. I don't know what the tension is. So let me go a step further and go for this particular pulley. Okay. So let's call this C. So if I draw a free body diagram for C, I'm going to remove this particular hinge joint. So there will be a force acting here, and I don't know the direction. I'm going to call it let's call it R, C. So since this thing has a force acting upwards over here, there'll be a force T acting downwards. Sorry, T by 2 downwards. Again, I need to look at, I have a cut here, so it's going to be a T by 2 downwards. And since this string is inextensible, there'll be T by 2 over here. So the reason why this is T by 2 is not because F equals ma, but the fact that this is a continuous cable and the force in the cable has to be the same no matter where I make the cut, right? The force, when I have it taut, when it's like this, the force is going to be the same over here, here, any point. And so that's why that's T divided by 2. Okay, now I can just use the fact that T divided by 2 is F, right? Why is that? That's because the force in this cable is given to me, it's F. Okay, so this is not F equals ma, this is just something which is given to me. I've given the force F. It's a function of time. So what I was after in this problem was to find T, right? Because if I know T, I can find the acceleration of A. But I know what T is now because T is just 2 times F. So let me write the equations of motion. Really, it's going to be one equation. So equation of motion for A. Okay, for A, there is T acting upwards, mass times gravity acts downwards, and then there is mass times acceleration acting upwards. Okay, but T is equal to 2 times F, so 2F minus MAG equals MAAY. Okay, so in this case, I know what F is. It's this plot. I know what mass is, what gravity is, I can find A by. So the next step is kinematics. So in interest of space, I'm going to start writing here. Okay, so how can I find the velocity? How can I find the velocity given the acceleration? Right, so you can integrate, right? So dvy dt is acceleration in the y direction. So it starts with as velocity equal to 0, and so integral dvy goes from 0 to vy equals ay dt, and what are the limits for the time? Are you sure? So this is 2, saying 0 to 2. Now there is an issue, however. The issue is that the force, right? So this force is increasing with time. It's 0 and goes all the way to whatever it is as per this plot. Okay, so at some point the cable actually slack. It's supposed to there's a force mg acting downwards, and as long as this force is less than mg, well, it's not mg, it's really 2f. So when this force is, let's look at this equation. Okay, when f is 0, right, this mass is not going to move up. It's not going to move up because unless f is greater than mg, well, 2f is greater than mg, mag, it's not going to move up, right? So if there is a take this. If this is 5 kgs, okay, there's a force 5 times g. Let's say 10 times. Let's say it's 10 kgs. 10 times g is 98.1. If I'm applying a force, I start the force from 0 and it's linear. When the force is 0, this thing is not going to move up. It goes to, it keeps increasing 0, 1, 2, 3, 4. Unless it goes to 98.1, this thing is not going to move up because the force acting downwards is more than the force I'm applying on top. So this particular thing will not start moving up till the force reaches a value equal to m times g. In this case, this particular block will not move up till this force equals 2f equals mag. So the block will move up when 2f becomes equal to mag. Okay. Before that, it will not move up, but it takes some time for the force to become equal to ma times g. So you got to first find the time it takes for the force to become equal to ma times g, and then change the limit here to correspond to that time. So what we're going to do is we can find what f is. So 2f is mag, so that f is mass is 400 times 9.81 divided by 2. That comes out to be what's that? It's 200. It's 196. 190. Can somebody calculate this? I think it's 981 times 2. 1962? Okay. So unless the force reaches that value, it's not going to move up. But we need to find the time at which the force reaches that value. So the way we do this is we're given F is 625 times t square. So 625 times t square equals 1962. And so if you want to solve for the time, using that equation, I get 1.772 seconds. So when the time equals 1.772, that's the time at which the force in the cable is going to be equal to mass times gravity. Okay. Okay, so what I need to do here is put 1.772. Okay, so the acceleration y is comes from this formula here. It is 2f or 2 times 625 t square minus mass is 400 times 9.81 divided by 400. And so what you can do is I take this, I shove it in this equation. That's going to be a function of only time, and then I can integrate that thing with respect to time. Okay, so that's just math. I'm not going to do that here. I'm just going to write the answer, and you got to go check this at home. So Vy equals, so I get 0.301 meters per second. Okay, so it's sort of a trick question. The force just has to reach a certain value, which is the weight of the mass, before it can start moving up. And that was, I guess, the trick part of this question. Is this clear? Okay, but other than that, it's very straightforward. Draw the free body diagram, write the equations of motion, and then solve for the kinematics. Same recipe. Okay, I have time for one more problem. Any questions? Okay. Okay, let's do a spring problem. Okay, so the 2-pound collar C fits loosely on a smooth shaft if the string is unstretched when S equals 0. So you're told that in this position, string is unstretched. Okay, what it means is that the force in the spring is equal to 0. Right? And the collar is given a velocity of 15 feet per second. So when the collar is in this position, it's unstretched, it's given a velocity of 15 feet per second. Find the velocity of the collar when S equals 1. So when the collar reaches this point, S equals 1, you're going to find the velocity of the collar. Okay, so the question is, do we need to do FPDs? Can we use the kinematics to solve for this?
Always need FPDs.
Because it's chapter 13. Okay, so the reason I need FPDs is because in this case, you need to, in order to find the velocity at a different time, you need the acceleration. You're not given the acceleration. It has to come from forces. The spring has a force. So that's why you need to do FPDs. The reason why I'm trying to emphasize this is because in an exam, when you see a problem, right, you will not know it comes from which chapter. For the finals, you will not know that. You'll have to first guess if you need to apply chapter 13 or chapter 12 and so on. So you have to first be clear what formula you need to apply, whether it's a plain kinematics problem or it's a kinetics, which is F equals ma problem. Okay. Now it's very obvious because it's part of chapter 13, so you know it's FPDs. Can't be anything else. Okay, so same recipe, FPDs. Okay, I'm going to draw the FPD for the collar because clearly I want the acceleration of the collar in order to figure out the velocity. Okay, so this is C. What I've done is I've removed the collar from the shaft. Okay, so the moment the shaft, the collar sits in the shaft, the moment I remove the collar, I need to replace the effect of the shaft with the force. Okay, now this is a planar problem, so there can only be two forces: the force in the x and the y direction. So the question is, would there be a force? Would the shaft exert a force in the x as well as y direction, or no? So there's no friction, okay? There's no friction. This is a friction-free problem. Now, will there be a force in this way from the shaft, or no? So the spring has a force acting in this direction. So that's obvious because clearly the spring has a force. When you stretch, it's going to create a force. My question to you is this right? Will there be two forces? There can only be two forces, right? X and Y. So somebody said no. Is this what's okay? One force is 0 actually. This force is 0. There's no force. There's only one force in the vertical direction. And the reason is this. When something is sliding in this direction, it's free to move, right? There's nothing preventing it from moving in that direction. There's no friction, so there's going to be no force. The reason why there's a force in the vertical direction is because if there was no force, then this collar would sink down. That cannot happen. The collar is being held in place by the shaft, so there's only a force in the normal direction. Okay? If there was friction, however, then there would be a force in this direction. There'll be a friction force like this. and the friction force always opposes motion, so it's going to be opposite to, in the direction opposite to the direction of motion, which is to the right. So there's no force because there's no friction. Okay, so that's the free body diagram. Okay, I am going to call this theta. This is theta, this is theta. Okay, I'm only interested in the motion in the x direction. So I don't care about writing the equations of motion in the y direction. I'm not told to find the normal force. So equation of motion. You could write the other equation, but it won't really help you in this particular problem unless you're asked to find the velocity, sorry, the force v. Fx is mass times acceleration in the x direction. So the net force in the x direction is Fs, the spring force, as I've shown it, times it's the component in the x direction. So it's Fs sine theta, and the force is in the opposite direction of motion. So it's negative. It's in the negative x direction. That is equal to mass times Ax. Okay, so I know the masses. I need to find what Fs is and what sine theta is. So Fs is k times, k is a spring constant. Yeah, it's given to be 4 lb per feet times the net stretch, right? The net stretch is going to be, so I'm going to draw this. I'm going to draw another diagram. This is not the free body diagram. It's just a sort of a diagram which shows me the lengths of the spring so that I can find this delta x. Okay, this is theta. This is the original position. That's 1. This is given as s. So this thing is, I need that for delta s. So what's this? So you can use Pythagoras theorem, right? That's s squared plus 1. Okay. So k delta x is going to be the length of the string in this position, the stretch position. So that's going to be s squared plus 1 minus the original length of the string, the unstretched length. The unstretched length is this. So I got Fs. I also need to find sine theta. Sine theta is simply the opposite side. So s divided by the hypotenuse square plus 1. So given that Ax is minus Fs, so minus k s squared plus 1 minus 1 divided by m times sine of theta, so s divided by s squared plus 1. Okay, so that's the acceleration. Okay, eventually I want to find the velocity. So I need to use the relation between velocity and acceleration, which is dv dt is a. So for the final step is kinematics. So dvx dt is ax. So v dvx integral from the initial velocity is 15 feet per second, so it's 15 here. The final velocity is asked, so that's an unknown, equals the acceleration, which is this thing here, k divided by m. The integral goes from 0 because the initial s distance is 0 all the way to s equals, I think it's 1 meter, or 1 foot times s squared plus 1 minus 1 times s divided by s squared plus 1. Okay, hold on. I think I used the wrong equation. I'm not interested in the time, right? I need to use this expression. Vx dvx dx. Sorry, in this case it's ds. Is ax. So what happens is this is going to be Vx dvx is this times ds. Okay, so only changes, this changes. Okay, so the left hand side I can integrate that. The right hand side is only a function of s. I know what the k is, what m is, and I can integrate that. And I will leave it to you to do it at home, but you can check. The Vx comes out to be 14.5 feet per second. Okay, this is after integrated. So again, to summarize, what we did here was draw the free body diagrams, write the equations of motion, only the equation which we care about, and finally use the kinematics to solve for the position and velocity.